Hi, my name is Ashley Nazema, and I'm presenting Lab 5. Today we're looking at the projectile motion of an object. This will be seen in the video later in the presentation. In the video, the object is a bouncy ball and is being tossed in an arc, so it moves in both the x and y direction. The relationship between the position and time of the ball represents the velocity. Given that there is no force to cause acceleration in the horizontal direction, this should be a straight line on a graph for the x direction. However, the line should be curved for the y direction due to acceleration caused by the force of gravity. Since the acceleration, velocity, mass, and time are known, Newton's second law of momentum was the best model to help predict the motion of the ball. The results of using this model was a prediction that matched the observation fairly well, but slightly undershot the observed motion. It was important to model projectile motion in the first place because we see it a lot in our real life, from sports to rockets. And from modeling, we can analyze this motion to better ourselves. We will further analyze the results later in the presentation. So to first understand the motion, we have to see that the x and y positions are different. The x direction has no acceleration, so the velocity is constant. However, the y direction does experience acceleration, so the position versus time graph forms a parabola. This is because the position equation itself is quadratic. So a constant acceleration and quadratic equation will result in a parabolic curve, as we see here. So here's the video of the ball. In this situation, the moving ball and the earth are the system. However, for calculating motion, we will include only the moving ball as the system and everything else as the surroundings. After collecting data from the video, I used these formulas to create the code to model the ball's motion. The net force is the sum of the forces, in this case gravity. Then, to update velocity, a manipulation of Newton's second law was used. Then this is manipulated even further to solve for the initial y velocity. So since v is 0 at the max height, we see that v initial is acceleration times time, which is g times t. The initial velocity in the x direction is constant, like in the formula in the previous slides. Then to update the position formula was used, with the final velocity as the average velocity since the force is not constant. All these formulas were then used in a code to create the computational model, also, which you can see here. There are also parts of my code that are commented out that have to do with drag and energy. Drag force is calculated by multiplying b times the speed squared, and energy change was determined by adding the change in potential energy to the change in kinetic energy, which is just mgh final minus mgh initial plus 1/2 mv squared final minus 1/2 mv squared initial. Both the drag and energy change will be uncommented later to give us data for later in the presentation. This code was then used to create the computational model. So here are the graphs comparing the observational data in orange with the model data in blue. As you can see, the model matches closely, but has a few discrepancies, one of them being that the model has a lower max height than the observed. I think that the way I did the center of mass may not have been exact each time, which is why there's a steeper slope than the model. However, I asked the TAs about this, and they also agreed after looking at my code that that's likely what it was. However, a more expected discrepancy would be if the model had a steeper slope than the observed. This would be because the model does not take into account drag, meaning it doesn't account for air resistance. So net force would be different in Newton's second law in this case if it had drag. However, as you can see, the model did fit the parabolic trajectory we expected for the y direction. Here we have a graph of the x direction, model in orange and observed in blue. As can be seen, the predicted line closely resembles the observed line. However, just looking at the graph, the observed line is not as straight. It has a few curves. This indicates the ball speed was not constant throughout. These discrepancies were likely caused by things the model could not account for, like breeze from the air conditioning, which would account for the dips you see because there'd be more of a resisting force, decreasing the velocity for that moment, and also uneven tracking on my part. To better this experiment and as a whole, I would redo it in an air-controlled room to smooth out the bumps in both curves, and to measure the center of mass accurately to track the ball's motion. To further the experiment, I looked at the model this time with drag in the y direction. As you can see, drag led to a lower max height. If the model had been steeper than the observed as expected, this would have been a more realistic because it would account for air resistance. Therefore, it would have been a better model by making it more realistic. Another way to look at this lab is to look at energy changes. We can see from the graph that total change in energy in orange is 0. This makes sense because if we remove air resistance, the only force acting on the ball's motion is gravity, which is a conservative force. So the total energy in the system is constant. This is why as kinetic energy increases in blue, the potential energy decreases in red. This supports the energy principle in which the change in energy equals total work done by the surroundings on the system. Since the system is the ball and the earth, there are no surroundings to even do work. This also supports the conservation of energy principle, which states that in a closed system, energy is conserved, which is what happened here. To conclude, this experiment showed that Newton's second law is useful in predicting projectile motion. This is because, as we saw, projectile motion is a combination of two different perpendicular directions, the horizontal and the vertical. As such, a manipulation of Newton's second law can be applied in the x direction and the y direction individually to model the motion. Therefore, it's important to study both models and real-life observations, if possible, to truly study and understand principles in physics.